Okay, so let's first go through the thermodynamics problem, a thermodynamic cycle, very famous problem, the regular gas engine. The Otto cycle is shown in the PV diagram below, consisting of two adiabatic steps from 1 to 2 and from 3 to 4. Those are two adiabatic steps, in addition to two isochoric steps from 2 to 3, and then back from 4 back to 1. Assume an ideal gas of n equals to 1 mole with a known ratio gamma of the respective specific heat values at constant pressure and constant volume of gamma equals to Cp over Cv. Determine the following quantities for each of the four steps, W, Q, and delta U. So this is in preparation for eventually calculating the efficiency. So let's first go through this. We're starting at step 1 to 2, 2 to 3, 3 to 4, and 4 to 1. Quoting work, heat, and the change in internal energy. So this is problem 1, part A. So let's first recall that the change in internal energy in integral form is the difference between heat and work, Q minus W. We have 1 mole. That simplifies our work a little bit, of an ideal gas. There's nothing set beyond that. So P times V, the equation of state for an ideal gas, is then equals to R times T. So let's first write down what we know about the step from 1 to 2 here. Since it's an adiabatic step, which means that the heat is equals to 0, Q1, 2, so I denote the step from 1 to 2 is equals to 0. That immediately allows us to relate the internal energy change and work. So therefore work 1, 2 equals to minus delta U 1, 2, but in an adiabatic step that equals to minus Cv equals to 2T minus T1. So now let's consider the step 2 to 3 here. In step 2 to 3, we just remind you of that, is carried out at constant volume, so therefore there's no work performed. So that's an isochoric step. With constant volume, so therefore dW equals to PdV is equals to 0, so W23 equals to 0, so therefore Q23 equals to minus del U23, so that since we have 1 mole, this equals to Cv equals to from 2 to 3, so T3 minus T2. Then another adiabatic step, and now it is a repeat in the overall argument, so I can be rather brief here. This is another adiabatic step. Adiabatic step Q34 equals to 0, so therefore W34 equals to minus delta U34 equals to minus C4 and then T4 minus T3. And last but not least, 4 to 1, again an isochoric step. So this is another isochoric step. At constant volume, so dW equals to PdV, so work is 0, so W for 1 equals to 0, and therefore Q for 1 equals to minus delta U for 1 equals to CV T1 minus T4. Always remember these differences, delta T final quantity minus initial quantity. All right, so let me just underline the important results here. So we have here now heat, we have the work, we have here now work, heat and change in internal energy, heat, work, change in internal energy, and then work, heat, and change in internal energy. All right, so far so good. So now let's worry about now part B, to show explicitly, and if you're being asked about this, what I want to show you is that delta U equals to delta U 1, 2 plus delta U 2, 3 plus delta U 3, 4 and delta U from 4 back to 1, that this is equals to 0. And remember, if you interpret the internal energy using the kinetic theory of a gas, then U is directly related to, can be formulated in terms of P and V. So a given state characterized by a combination of pressure and volume characterizes the internal energy. So you're changing the internal energy as you hop along. But then eventually when you go back from 1 to 2 to 3 to 4 and back to 1, then the overall change, since you compared to the same combination of pressure and volume, is actually 0. So let's show this explicitly. So now we just use our results from up here. So then what do we have? So minus delta U12 equals to minus CV T2 minus T1. So we have here C4 T2 minus T1. Then we have delta 2, 3. Delta 2, 3 is here. This is now plus CV T3 minus T2. Plus now delta 3, 4. So the same argument is now T4 minus T3. So it's CV T4 minus T3. And last but not least, plus C4 T1 minus T4. So now we can take CV out here and then have T2 minus T1 plus T3 minus T2 from here, and then here we have plus T4 minus T3 from here, plus T1 minus T4 from here. So now we can combine various terms here. So this term with this term, T1 with T1, T3 with T3, and T4 with T4. And you immediately see that they all cancel. T2 minus T2 minus T1 plus T1, T3 minus T3, and T4 minus T4. So this here is equals to overall 0. So therefore we show that delta U equals to 0. So that's an important result. Okay, so that's this. Now, let me just label this here. So now we come to the second part here, namely evaluating the efficiency. Show that the efficiency is given by. All right, so now, part C. Part C is now what? So the efficiency, this is something which I'm expecting you to know what efficiency really means. So the total amount of work performed, so what you, so to say, get out of that, and what you invest in the amount of heat input into the system. So therefore, we add up all individual work contribution, W12 plus W23 plus W34 plus W41 divided by, well, and now let's think a little bit. Divided by what? Well, in the adiabatic step, Q12 and Q34 is 0. So we have here two non-zero heat contributions. We have Q23, which is T3 minus T2. T3 is clearly at a higher temperature than T2. It's a higher pressure. Isolines are behaving, dropping down like 1 over T here for an ideal gas. So this would be at a higher temperature than T2. So T3 minus T2 would be clearly larger than 0. Now here we have another non-zero heat contribution, Q41, which is T1 minus T4. T1 minus T4, but T4 is at a higher temperature than T1. So therefore, T1 minus T4 would be less than 0, whereas Q23 would be larger than 0. So therefore, it's very clear we have to divide this now by Q23. And the rest is a little bit of algebra now. So now what do we have? And also here now, one thing which will simplify quite a bit is that there are two work contributions which are 0. Q23 is 0 and Q41 is 0. So therefore, what do we have? We have Q12, which is minus C4 T2 minus T1. So we have here minus C4 T2 minus T1. Q23 is 0, and then we have one more plus Q34, which is minus C4 T4 minus T3. T4 minus T3, and then we're dividing this by Q23, and Q23 is given here, C4 T3 minus T2. C4 T3 minus T2. All right, so let's simplify this algebraically now a little bit. You can, of course, cancel out all C4s here. Then we have here minus, so it's multiply this minus sign in here, so then we have here T1 minus T2. Here we have another minus sign multiplying this, and then we have here plus T3 minus T4 divided by T3 minus T2. So what is this now? So now we can rearrange this a little bit. So you have then here T3 minus T2, T3 minus T2, the same as the denominator expression, T3 minus T2, to come to an expression of 1 minus something. And then we can write the numerator remaining portion as minus. There's a T4 here, T4. But there's a plus 1, but we write here as minus T1 here, minus then plus. So therefore we have then eta, we can write this then as 1 minus, dividing then T3 minus T1 is 1, and minus T4 minus T1, T4 minus T1 divided by T3 minus T2. And this is exactly what was given, T4 minus T1, T3 minus T2. Okay. But as you can see, you have everything so far now formulated in terms of temperatures. And as I said in class, temperature is not necessarily quantities which you necessarily have access to. But in a regular engine, the two volumes here, V1, V4, which are identical in V2, V3. So before the piston moves, compresses the gas here, that volume is very well defined by design, and also this volume is very well defined by design. So the idea is now to formulate this whole expression rather than in temperatures, in terms of volumes. And there, this requires a little bit of thought now. So let's first recall what we know. So we need to relate temperatures and volumes. But let's first recall what we know about the volumes. V2 equals to V3, and V1 equals to V4. So now, V2 equals to V3. This is purely a fact that we have here two isocores. That means V1 equals to V4. Then how can we relate now temperature and volume? So this is an adiabatic steps, and this is an adiabatic step here. And we can relate now state variables in 1 to 2, namely temperature and volume, through unique relations for adiabatic steps, which we derived in class and which you have in your equation sheet, which namely state that T times V to the power of gamma minus 1 is a constant. So what does this now mean? So then we can relate 1 to 2 and then 3 to 4. So we have then T1 times V1 to the power of gamma minus 1 equals to T2 times V2 to the power of gamma minus 1. And we also know that T4 times V4 to the power of gamma minus 1 equals to T3 times V3 to the power of gamma minus 1. But now that we know that V2 and V3 is the same, so these quantities and this quantity is the same, and V4 and V1 is the same, then we can also write this in the following way. Namely as, so if I divide out now here T1 divided by T2, then what do we have here? We have here now T1 divided by V2, then we have here V2 divided by V1 to the power of gamma minus 1. However, V2 equals to V3 and V1 equals to V4 to the power of gamma minus 1. But V3 divided by V4 is nothing else than T4 divided by T3. So now compare the very left and the very right hand side. So this is what we're now making use of. So therefore T4 equals to T1 times T3 divided by T2. And therefore we can write the efficiency now in the following form. Eta equals to 1 minus T4 minus T1, T3 minus T2. So then we have here minus 1 minus, and we replace now this expression for temperature, this ratio T1, T3 divided by T2 minus T1 divided by T3 minus T2 here. So let's see how we continue with this now. So let me rewrite this expression now. So I'm rewriting this here, but I'm multiplying now using a common denominator, T3 minus T2. We have then up here minus T1, T3 over T2, but then we would have here plus 1 divided by T3 minus T2. So we have then T3 minus T2, and then we have here T3 minus T2 minus T1 times T3 divided by T2 plus T1. And now let's multiply numerator and denominator by T2, just to get rid of this fraction here, T2. Then we would have, and this is some very simple algebra now, then we have products of temperatures, T3, T2, from here, minus T2 times T2, minus T1, T3, plus T1, T2, divided by T3, T2, minus T2, T2. So now Let's form some ratios here, where we are now taking out, this is T3, this is T3 minus T2 times T2. So now I have here also T3 minus T2. So I take T2 out times T2 minus, and then we have here T3 minus T2. I'm taking T1 out. So let me just circle this here. So here is T2, and here it is T1. To have a same difference, namely T3 minus T2 from here, T3 minus T2 from here, and then T3 minus T2, I'm getting this if I'm taking T2 out. So therefore, these expressions cancel. These differences, T3 minus T2. And what we have is then something very simple. 1 minus T1 divided by T2. And that we can now easily relate, again, T1 over T2 to V2 divided by V1. And V2 over V1 is just the ratio after the class has been compressed before in uncompressed form. So V2 over V1 to the power of gamma minus 1. So we can write this at 1 minus V2 over V1 to the power of gamma minus 1. And then with what you usually do, quoting this as a compression ratio, namely R equals to V1 divided by V2. And therefore you have the efficiency as 1 minus, so this is here 1 over V2R, so therefore we have here then 1 over R to the power of gamma minus 1. Okay. So in summary, let's just review this for a second, what we have done. The problem is significantly simplified since I use one more of an ideal gas. Here's the ideal gas equation. I have here now the two adiabatic steps. Heat is 0, therefore you can right away relate work and the change in internal energy. For steps 2 and 3 and 4 to 1, you have isochoric steps. The work is 0. We can relate heat and the change in internal energy. Then we showed explicitly that in the sum of all internal energies from one step to the next, in the total sum, that this is equals to 0. Then we evaluated the efficiency as the total work done divided by the heat supply, Q in, which we identified as Q23. We evaluated this simply using our expressions from here and came to this expression which was given in the problem. Then we used the fact that we have two isochoric steps, V2 and V3 is the same, and V1 and V4 is the same. And relating unique adiabatic relations between T and V, namely steps 1 and 2, 1 to 2, and then 3 to 4. And then use those, which allowed us to rewrite then T1 over T2 as T4 over T3, and you eliminate T4 to come then to an expression involving only 1 and 2, and using the fact that the compression ratio is V1 over V2, and you can also write this as 1 over R to the power of gamma minus 1. So that's it.